All right, good afternoon, everybody. Welcome back to Intro to Physics. This is day 4, our last day for this week. So remember, tomorrow on Friday, we do not meet together for class. There is an enrichment session instead. Now, keep in mind, these enrichment sessions are optional. You do not have to attend by any means. But if the topic is something that seems interesting to you or relevant to you, then I definitely recommend that you check them out. They are also on Zoom, and it is a separate Zoom link than the one for our class. Now, she posted an announcement on Canvas just after 2 p.m. today. So if you didn't get an email about it, check on our Canvas page in the announcements section. So let me just read the details for you here. The first enrichment session is about freshman year experience and Evans Library. Freshman year experience is a class, a 1-credit class that you will take your freshman year just to kind of orient you to the campus and get you situated, I suppose. And then Evans Library is the library that we have on campus. It has a ton of resources for you. So I definitely recommend that you check out this enrichment session if you're able to. So the link for it is in that announcement that has been posted on Canvas, possibly also emailed to you, but it's tomorrow at 10:30 a.m. Eastern time. Okay, so again, that link is there for you in the announcement or possibly in the email that was sent out. There's another question in the chat. The Monday after next week is no class. So the Monday after next week would be the 4th of July. And that's correct. There is no class on the 4th of July. You can enjoy your holiday. But we do have class next week on Monday, just not the following week. Do you guys have any questions about that enrichment session? Okay, cool. Well, hopefully you guys will check it out. And if you're unable to, then there should probably be a recording of it somewhere, and I can get that to you if you would like. All right, well, we will jump back in to where we left off yesterday. We were talking about vectors yesterday, and okay, so I want to start off with a example problem for you guys to try yourself. So can you guys all see my give it a try problem? Good, general nods, awesome. Okay, so take a look at this question really quickly. Think about what we talked about for vectors yesterday. I'll give you just a quick minute to answer this question on your own, and then we'll go through the answer together. Okie dokie. So hopefully that was enough time for you to think through this problem, which is about setting up equations to figure out the components of this velocity. Remember, velocity is a vector. Vectors have 2 parts to them. They have a magnitude or the size and a direction that's associated with them, and both are equally important. Okay, so for this velocity vector, we need the magnitude and the direction, which we have. We want to break that down into its components to see how far north he is running and how far east, well, how fast east he is running. And A is our correct answer, right? So in this case, if we set it up in a diagram, draw our triangle out like we had been doing yesterday, that hypotenuse of the triangle or the vector itself would be 19 meters per second. And then to find the side of the triangle that is opposite our angle, we'll use the sine of our angle. Remember SOHCAHTOA, sine is opposite over hypotenuse. Okay, so the opposite side is the hypotenuse times the sine. And then to find the horizontal component or that eastward component, we'll use the cosine because that side of the triangle is adjacent to the angle that we're interested in. And the cosine is the adjacent over the hypotenuse. Yes, there's a question.
I feel like I would understand this question better if I was pretty lost in the nine in the like with the 100 105 degrees counterclockwise from the east. I understand east and I understand counterclockwise, but I don't understand how it translates. Like my brain is not really understanding how it translates to like north equaling the sign of 105
Yeah, so
slash.
that's why I always recommend that you start by drawing a picture because I really think it's easier to visualize when you have a picture in front of you. So if we have our axes, and for me, this side is east. I, I don't know if my video is mirrored for you guys or not, but over here is east. And so we always want to measure our angles, or the standard way to measure our angles is counterclockwise from east. So we know that straight north would be 90 degrees and 105 degrees would be just past 90 degrees straight up. But this is still in the portion of the graph that is above our x-axis. So it's still like a positive direction.
It's still in quadrant 1.
It is in quadrant 2.
Oh,
I think if I have my quadrants right. Yeah, so it's because it's past 90 degrees. So anything between 0 and 90 would be our quadrant 1. And between 90 and 180 is quadrant 2. And so 105 would be somewhere in that quadrant 2. So it's still in the north direction. It's actually westward as opposed to eastward, but we would find that out after we do our calculation. So I have a follow-up question to this one, which we'll go into more detail about the same example. So I'm going to go ahead to that follow-up question. And then if you still have questions about it at the end, I would be happy to kind of work through that with you. Okay, so same scenario, still running 19 meters per second in that direction. So what do we do if we get these particular components? Okay, an x velocity of negative 4.92 meters per second and a y velocity component of 18.4 meters per second. What does that mean? So take a look at those choices and come up with your guess. All right, so I'm seeing some answers coming into the chat. Let's go through this together then. The correct answer is C. So for those of you who shared your answers in the chat, good job. A negative velocity eastward means that we're actually traveling westward, right? But we have a positive y component, which means he would be traveling northward as well. Okay, south would be a negative velocity, a negative direction.
I'm still confused.
Did you draw out your picture yet?
Mm.
Give that a try. And I think there's one more follow-up question to this example. Okay, so in this case, how do we find the magnitude and direction of the following velocity? Right, here are the two components that we would have found from the first part of this example. So we have these components. How do we find the magnitude and direction? Is the magnitude the Pythagorean theorem on the velocities and then direction inverse tangent of y over x? Or B, magnitude is the sum of the velocities and the direction is the tangent of y over x? Or is it C, the magnitude is the Pythagorean theorem of the velocities and the direction is the inverse tangent of x over y? Think carefully. All right, I'm seeing some answers coming into the chat. And all of those answers that I saw are correct. Good, it is part A. So whenever we want to find the magnitude using our components, we'll use the Pythagorean theorem. So remember, that's the square root of our x component squared plus our y component squared. And that will give us the magnitude, how fast he is going, which we already knew from the problem. The direction we could find by using the inverse tangent of the y component over the x component. Okay, that's different than option C, which is the inverse tangent of x over y. So just read those carefully if you're ever in a test situation. Okay. Again, if you have further questions about these examples, I'd be happy to go through them with you in more detail at the end of class. But I do want to just draw your attention once again to some of these quick check. These would be like quiz type problems, maybe homework type problems that you guys can take a look at. We don't have time to go through them right now, but this PowerPoint will be posted on Canvas for you. In fact, I think it already is posted on Canvas for you, so that on your own time you can go through these questions, make sure that you understand this particular topic, and then I'll post the answers for them as well. Okay. And then these bonus activities are the ones that I mentioned yesterday. They are open and available for you on Canvas. I will be posting answers to all of the practice assignments from this week. I'll be posting them tomorrow so that you have access to them. Check your work over the weekend. If you have problems with anything, you can send me an email and I'd be happy to address whatever questions you might have. But do you have any questions before we move on to our topic of the day?
Yes, like I'm trying to draw a picture and I'm just really confused. I'm like visualizing it is hard, and like drawing a picture of it is just frustrating.
Okay, well, save that frustration for the end. I don't have like a pencil and paper handy right now. So once I stop the recording, I'll go grab some and come back and I'll show you how we can draw this picture. But that will be at the end of class. Don't let me forget.
I won't let you, but I'm just really confused, like counterclockwise eastward. I'm not really used to that. I'm just used to using like either northeast.
Yeah, I know it is a different thing to try to get used to, but again, I will be happy to go through it one-on-one with you at the end of class today.
Okay.
Okay. Great. So let me go ahead and pull up the PowerPoint for today, which is a different topic. We're moving on to chapter 2 now. Can you all see my PowerPoint for chapter 2? Good. Thank you, Victor, for your vigorous nod. Yeah. Okay, so we're going to be talking about motion in one dimension for today, motion in a straight line. So there's, of course, our cat picture for the day. Now, I will say that this chapter, or at least this portion of it today and the next couple of days that we meet together, is pretty graphing heavy. So if you have graph paper at home that you can kind of follow along with, that would be helpful. If not, a freehand graph is totally acceptable too. But we will be putting your graphing skills into play today. All right, so this kind of initial question that we have, how do you know something is moving? I want you to just take a quick second and think about that. Maybe type an answer into the chat, that would be helpful, or you can respond vocally as well. How do you know if something is moving?
It will show its velocity and direction.
Okay. Cool, good answer. When a force is acting upon it, okay, it has velocity or displacement, nice. An object is considered moving when its position changes over time, good. When its velocity is not zero, awesome. Yeah, these are all great answers. Looking at it, clever. Potentially looking at it, cool. Yeah, so there are definitely a lot of different ways to know when something is moving, but it's sort of an interesting question to like stop and think about for a second. Okay, here's another kind of question pertaining to how we describe motion. How far does an airplane travel down a runway before it reaches takeoff speed? Okay, that sort of question is what we're going to be able to answer by the end of today and the next couple of days. Another question that we should be able to answer by the end, when you throw a baseball straight up, how high does it go? And another one, when you drop your phone, how much time do you have to catch it before it shatters on the ground? Obviously a very important question, especially if you have small children around. Anyway, so when we analyze motion, there are a couple of things that we need to keep in mind, just so we're on the same page terminology wise. Okay, so here is your happy smiling face because you love physics so much. Okay, so when we're describing motion or analyzing motion, what we want to do is set up a coordinate system to give us a frame of reference, because we can't really tell if something is moving by looking at it unless we have established a frame of reference. So unless we're looking at a stationary background, and then we can see that that object is moving along a stationary background, then we can know it's moving. But we need that coordinate system to give us that frame of reference, that perspective, so that we can analyze the motion properly. This coordinate system is going to show us where the origin is, right? So in the case of graphing, that's right where the axes cross, where both variables are 0. It's also sometimes called the 0 point for that reason. And then in our coordinate system, we're going to need to define which directions are positive and which are negative. So the standard rule of thumb is that up and right are positive and down and left are negative. However, that doesn't always have to be the case. You can choose whatever is most convenient for your situation as long as you remain consistent. Okay. We're also going to define position to be the separation between your object and the origin. And in this case, it's the x direction. So position will get the variable x. Okay, that separation between the object and the origin. Okay, and position can be positive or negative depending on the scenarios. We'll get into that in just a moment. Okay. Another thing to keep in mind, just a quick reminder from yesterday when we were talking about vectors and scalars and that sort of thing, is this idea of speed versus velocity. Now, speed is a scalar. So what does that mean again? What is a scalar?
Scalars are units that only measure one part and don't have like two parts to them, like
What is the part
magnitude
that they
and
do
direction.
not have?
It's direction, but they always have magnitude.
That's right, exactly. So speed is a scalar, meaning we only care about the size, right? We don't care about the direction. So if the police are trying to catch you speeding, they don't care what direction you're going. They just care how fast you're going, right? Velocity, on the other hand, that's the vector. That's where direction makes a difference. We need to have the direction component to be considering a velocity. Okay, so when we're in the car, the speedometer plus your compass, if your car has one, will tell you your velocity. Okay, and then again, our standard rule of thumb here, right or east, north or up or forward, those are all going to be our positive directions for the most part. And then left, west, south, down, backwards, those sorts of directions, most commonly are going to be your negative directions. Okay. Now, that being said, there are different kinds of velocity that we will talk about as well. So the first type of velocity that we have is the average velocity, and that's our total displacement divided by the total time. So remember, displacement is a vector as well. It tells us how far away we are from our starting point and in what direction. Okay, so this average velocity is that total displacement divided by the total amount of time that you took to travel there. So it's the rate at which the rate at which an object changes its position from one place to another, right? Again, how fast it is going in a particular direction. It is a vector because all velocities are vector quantities. And the typical units that we'll see for this are some distance unit divided by some time unit. So most commonly you'll see meters per second. Depending on where you live, you might be more familiar with miles per hour or kilometers per hour. But any distance unit divided by time unit is the unit that we can use for velocity. Now here in this green dashed box, I have the typical equation for you. Average velocity, or V average, equals that triangle symbol is called delta, and that tells us the change in something. So you probably have seen this symbol before in like chemistry. If you've taken chemistry, they use the change in a lot. So we have the change in our delta x over delta t, the change in our x position divided by our time increment. Okay. So let's say, for example, if it takes 3 hours to drive to Miami, which is 300 kilometers away, the speed is 100 kilometers per hour. The average velocity is 100 kilometers per hour south, because Miami is south from Melbourne. Okay. If I drive there and back, the total distance that I am traveling is 300 plus 300, so 600. However, my displacement is 0, right? Because I'm ending up at the exact same place that I'm starting. So my displacement is 0, which means no matter how long you might have stayed in Miami, your average velocity is 0 because your delta x, your change in position, is 0. Your average speed is not 0 though. Because the total distance that you traveled was 600 divided by your time increment. Okay, so just keep in mind as we go, speed and velocity are similar, but they are not the same thing as each other. Okay, here's an example for you. A race car starts a race. 1 second after the start, it is at a point 19 meters from the starting line. At 4 seconds, it is at 277 meters from the starting line. What is its average velocity during this time interval? And now we're going to go through this example together because you don't see that cat in the corner. So let's walk through this example together. Okay, here's our picture. Because again, I always recommend that you start by drawing a picture whenever possible. So we have here our starting point. And then P1, the first point of interest, is 1 second after the race starts. So we know that that is at a position of 19 meters from the origin or from the starting line. The second point of interest is P2, and that's at a position of 277 meters from the starting line. So to find the average velocity, remember, we're going to take the change in our position divided by the change in our time, or our time interval. Right, so we have 277 meters minus 19 meters. That'll give us the difference in position divided by that time interval. So at that second point, it was at 4 seconds. The first point was at 1 second. The difference between those is 3. And so we get an average velocity of 86 meters per second. Is that answer complete?
Yes.
What might we be missing?
I suppose you could add a direction, but it kind of already has one because it's positive.
Right. I'm so glad you mentioned that. Yes, we could explicitly, I suppose, mention the direction, right or forward, maybe as a direction. But the direction is also implicit in our answer because it is positive, and positive is a direction, kind of, right? Just like negative would tell us about the direction as well. Good.
So it's going 86 meters per second in to the right.
Yes, according to the picture, it's traveling to the right. Yep. Cool. Okay, so some rules for average x velocity. Remember, we're just concerned with motion in one direction right now. So we're just talking about x velocity at the moment. So our average x velocity is positive if x, meaning position, is positive and increasing, or if x is negative and becoming less negative, right? So imagine in your head a number line, or like on your graph here, which is sort of a number line. If it's starting at a negative position and becoming less negative, then it's still moving toward the right, which is a positive direction. Okay. Or if it's just moving in the positive x direction, all of those things would imply a positive velocity. So on the flip side, our average velocity would be negative if our position is positive but decreasing, so going back towards the origin, or if our position is negative and becoming more negative, again, that's going away from the origin in that negative direction. Again, you can choose the positive direction to be whatever is most convenient for you in the particular scenario, but you have to keep it consistent for the entire problem. So if it's more convenient to make left the positive direction, you are free to do so. Just keep it that way the entire time. Okay, so one type of graph that we will make in Physics 1 is an XT graph, or a position time graph. So remember, our definition of average velocity is that change in position over the change in time. So if we graph the motion of the object's position over time, that is our position time graph, or an XT graph. Okay, so let's create one for our scenario. So when we make graphs and label graphs, we are always going to use the convention of like y versus x. So an XT graph means that x position is on the y axis and time is on the x axis. And this can get confusing, right? Because here x is a direction and it is a variable position. So just remember, when we're naming these graphs, XT graph, x means position, and that goes on the y axis.
For me, it's easier to remember it like this. T, time, is an independent variable, while x, your displacement or your movement, is a dependent variable on you. So while time is still going, it's independent of you, while where you are, where you are, your displacement, your meters, is dependent on you and how fast you go, you know?
That's exactly right. Yep. Our independent variable goes on the x-axis and our dependent variable goes on the y-axis. Absolutely. Okay. So here's a bird's eye view of our race car from the previous example, right? Point 1 was 19 meters in front of our starting point. And then point 2 is 277 meters. Now, if we actually graph the motion of this race car over time, we'll see that it is a curved line. And that's because the race car has to speed up initially, right? It doesn't just jump out of the gate going 86 meters per second or however fast it's going. It has to speed up to that point. So it's going to cover a smaller distance each second initially than it will once it's reached its full speed. Okay, so here's that same graph with just some points labeled instead of just kind of visualized.
To get each
so-
point, may I say something?
Sure.
To get each point on the graph, you would have to use calculus to calculate the blue line right there.
Yes, and I will teach you that calculus in a little bit. It's not bad. If you haven't taken calculus, you'll be fine. It's okay. So for our displacement along the x-axis, the object's average x velocity is the slope of the line that connects those 2 points of interest. Right? If we remember from probably algebra 1 is where you learned about like the slope of the line. And that would be the change in y, or the rise, divided by the change in the x variable, or the run. So rise over run is our slope. And in this case, that is the change in position over the change in time. And would you look at that? That's our equation for average velocity. So if we connect those 2 points of interest with a line and find the slope of that line, that gives us our average velocity during that time interval. So a key thing to remember, if you're taking notes, write this down. The slope of a position time graph gives you the x velocity.
Miss Zamora, I have a question about the name of the x velocity.
Okay.
How come you just call it the x velocity, and why not just call it velocity?
You could, but once we get into motion in more than one direction at a time, then you'll want to be in the habit of kind of specifying which direction you're talking about. That will be next week when we do projectile motion.
Oh. Is
Mhm.
So that means if it's called x velocity, it's I might be just thinking too hard about it.
You could also call it horizontal velocity, right? Because our x direction is horizontal and our y direction is vertical. So you could just easily call it the horizontal velocity.
Okay.
So there's a question in the chat here. If you were given a position equation and were asked to find velocity, could you just take the derivative? Does that rule apply here as well? Absolutely, it does. Vanessa, if you know how to take derivatives, yes, that is essentially what we are doing. If you don't know how to take derivatives, that's what I'm teaching you how to do right now, essentially. Okay, so our second type of velocity is the instantaneous velocity. So the instantaneous velocity is how fast an object is moving at a particular point along its path. So we're not looking necessarily at the entire pathway anymore, or 2 points of interest. We're looking at just one particular point of interest. And this is the type of velocity that we will most commonly be referring to. So typically it's just called velocity as opposed to average velocity. So really our instantaneous velocity, if you think about it mathematically, is the average velocity between 2 points as the time interval between them approaches 0. So as these points are getting closer and closer together in time, that the average velocity between those 2 points, how that is changing, is our instantaneous velocity. So that would be this equation in the green box here. Velocity in the x direction is the limit as the change in time approaches 0 of our change in position divided by the change in time. Now in calculus, you will see this written as dx over dt, and that stands for a derivative. So here's where, if you've taken calculus before, or AP Physics, IB Physics, something like that, you will probably be familiar with dx over dt notation.
Oh,
if not, then here's your introduction to it. Yes.
I'm more familiar of having like having y and then with a tick next to it equals to.
Yes, absolutely. And I will go into different notations for derivatives as well. Okay, so once again, here is our race car example from before, and our position time graph that we saw previously. So as time goes on, and the interval of time shrinks, the slope of the line connecting the 2 points gets steeper. So here's our initial, like the starting line point, that blue dot, and its finishing point. If we want to find more the instantaneous velocity, as this dot gets closer and closer on the graph to our final point, we can see the slope of the line connecting those 2 points is getting steeper and steeper and steeper. So eventually those 2 points of interest will get so close together that they are the same point. That's our instantaneous velocity. So the velocity at the instant where those 2 position dots meet on our graph is our point of interest, right? So there would be no space between those 2 positions. The line only touches the curve at that particular location of interest. When that happens, that black line there, that's called a tangent line, because tangent means it's touching the curve at only one location. And so the slope of that black line would be our instantaneous velocity, or the velocity of the object at that particular instant. So when we find the slope of that tangent line, that's a derivative. Congratulations, you've done calculus. Woohoo! Okay, so just a quick note on sign convention here. Time interval is always going to be positive. We won't be going backwards in time. Time doesn't go backwards. Time always, for our purposes, goes forward. Right, so our time interval is always going to be positive. The x velocity has the same sign as the change in the position. So if your object is going forward or in a positive direction, then you will have a positive x velocity. If it is going backwards, you will have a negative x velocity. Right, so a positive x velocity means that its position is increasing, motion is in the positive x direction, and so you'll end up with a positive slope on your graph. So that would be an example where an object is moving forward, like the race car driving forward. A negative x velocity would mean that position is decreasing or motion is in a negative x direction. And so you would end up with a negative slope. So that would be where the object is moving backwards towards the starting line. Okay, so if your car was like in front of the starting line and then it had to move backwards to get to the starting line, that would be a negative x velocity. So here's an example of that graphically. Right, so these first 2 pictures, these first 2 graphs, if you kind of take your pencil or take your finger and follow it along the tangent line to the curve, all of those points would give you a positive slope. Same thing with that second distance versus time graph. All of those are giving you a positive slope. But that third graph, if you follow your finger down it, that would be giving you a negative slope. Right, so that would be a negative x velocity. An object can have a positive position, but a negative x velocity, or vice versa, right? What matters more is that change in the position, right? X, or position, tells us where the object is, but that velocity tells us how it is then moving. Okay, we'll get lots of practice doing this and next week as well.
I have one question though.
Okay.
I feel like I got a little bit confused when you said the last part. An object can have a positive x and a negative x velocity. Can you say that again in a lot of I got it, but like I got a little bit confused.
So a positive x, remember, that means position, a positive position. So let's imagine you are the race car and you're in that race. You can be in front of the starting line and driving backwards. That is totally a plausible scenario. So if you are in front of the starting line, that would be a positive position. But if you're driving backwards, that's a negative x velocity. Right? So it is possible to have a positive position, but a negative velocity. It depends on your motion, the change in your position. There's a position, yeah, go ahead.
So you would be like you would be starting out in the positives,
Mhm.
then you would be just going backwards.
Yeah, that's one example.
Okay, I'm getting it.
Okay, good. That's what I like to hear. There's a question in the chat too. Will we get into integration with this too? Like how integrating the velocity gives displacement and integrating acceleration gives velocity? Yes, we will. Ha, we'll get there. Okay. So some shapes that you'll see for your position time graphs, they can have all different shapes. So, I mean, in the last slide right there, we saw 3 different shapes that it could have. Now, those are all curves, but they're all curving in different ways. And those all tell us really important details about the motion of the object. So we could have flat lines or straight lines or curved lines or a combination of all different shapes in the same graph. But no matter what shape the graph is, we call it a curve. Unfortunately, even if it's a straight line, it's called a curve. And the velocity is always the slope of the position time graph at that location. So if you don't have the equation for slope memorized, I highly recommend that you write it down because we will be using this equation a lot over the next few days. So slope is rise over run. So that change in the y divided by the change in the x variable. Now, if the slope of our graph is getting steeper, so either positively or negatively, that means the velocity's magnitude is increasing. So the object would be speeding up in some direction, either forward or backward. It depends on the scenario. Yes, did you have a question?
Oh no, I just had a comment.
Okay.
Like where I come from, they call it slope formula.
Ah, cool. Okay. So here's an example. What is the velocity of this object? Okay, so again, we have a position versus time graph. And we should remember, because I've literally just been saying it, that the velocity is the slope of a position time graph. Right? So we're going to figure out how much the graph is going up between our 2 points of interest, how much it is going over. So the rise divided by the run. Okay, so in this case, since we're not given a specific time interval to look at, we'll just look at the entirety of the graph. Now, in doing that, technically I'm taking the average velocity, but since this graph is a straight line, the slope stays the same the whole time. So the velocity at any given instant in this example is the same as the average velocity, right? So in this example, the object is going up or going forward a position of 50 meters. So 50 minus our initial point 0. And it does that in a 5-second time interval. So 5 seconds divided by 0, I'm sorry, minus 0 seconds gives us a velocity of 10 meters per second. Good. And our direction is sort of implied in this, right? It's a positive velocity, so it's going in whatever forward positive direction we're dealing with. Okay, here's another example. I want you to give this one a try on your own, and then we'll come back together and go through the answer together. So example 3, what is the velocity of the object during each stage of its motion according to this particular position time graph? And then what is its average velocity over the whole trip? So I'm going to give you a couple of minutes to think through this on your own, and then we'll come back together and go through the answer. All right, so let's take a look at each of these segments individually, and then we'll take a look at the graph as a whole. So stage 1 of its motion, that first section between 0 and 5 seconds, we can see it goes a position difference of 5 meters, right? Because it ends up at 5 meters. It started at 0 meters, so that's a change of 5 meters. In a change of time, of 5 seconds. Okay, so for the slope for that section, it is 1 meter per second. The second stage of its journey is this section right here. So from 5 seconds to 10 seconds. And we can see that the slope of this line is 0, right? It is not changing its position at all during this time interval. So even though time is passing, even though 5 seconds have passed, its position has not changed. And if velocity is the change in position over the change in time, and its position is not changing, then we have a velocity of 0. Stage 3 is from 10 seconds to 12.5 seconds when it hits that axis again. And we can see that it changes from 5 meters to 0 meters. Right, so be careful here how you plug your numbers into that equation. It is ending up at 0 meters and it started at 5 meters, which is a change of position of -5 meters. Right? It has gone backwards, back to starting line. And it has done that in 2.5 seconds. So -5 divided by 2.5 gives us -2 meters per second as our velocity for that stage. Yes, is there a question?
With me, it's like my teachers always told me with salt formula that it never mattered how you put in the numbers, but like now seeing that it's like because they ended up with like 2 meters per second instead of -2 meters per second.
It does matter unless you are specifying explicitly the direction that it is traveling. So I wrote it as -2 meters per second because that negative tells you explicitly the direction, right? You could also say 2 meters per second backwards or something like that. As long as you specify the direction in writing, then you could have your answer as a positive 2 meters per second. But there needs to be some indication of direction in order for this to be considered a velocity. Otherwise, it's just a speed. And that's not what we're looking for. Right?
Yeah.
Yes.
I mean, it's pretty obvious on the graph. Since it's going down, it's going backwards.
Right. Yes. Pictures do help. And then its average velocity over the entire trip. Remember, we're considering the entire change of position there for the whole trip. It's starting at a position of 0. It's ending at a position of 0. And it does that in 12.5 seconds. But since it ended up at the same place that it started, its average velocity is 0 for the entire trip. Okay. Any questions about this example? I mean, if this seems super straightforward, that's awesome because technically you are doing calculus right now. That's pretty cool. Okay. So just a couple quick follow-up questions to this then. What is the object's total distance that it has traveled? And what is its displacement? Take a quick minute and think through those answers as well. I'll give you about 20 more seconds. Okay, so let's take a look at these answers. The distance that it is traveling, remember, is all of the pathways added together, all of those distance portions added together. Now, initially, it's traveling 5 meters, and then it stops changing position, and then it goes back 5 meters. So that's a total distance of 10 meters that it has traveled. Okay. On the other hand, its displacement is 0 meters because displacement is only concerned with where it started compared to where it ends up. And since it's starting and ending up at the same place, its displacement is 0. Woo. Okay. We have a couple minutes left. Let's do this. I think this is the last example that I have for you guys, example 4. So try to describe in words what is happening to the object that creates this graph, both in terms of its position and its velocity. So take a look at the graph. What might this object be doing?
Can I answer this one?
Not yet. Take about 30 seconds, let everybody think through it, and then we'll come back together and share some answers. Make sure you have thought through both the position and the velocity, what might be happening here. Okie dokie, you can go ahead and share your answer.
Okay. So what I see happening on the graph is in the first half of the graph, it's speeding up and it's getting farther and farther in distance. Then on the second half of the graph, it's slowing down and going back to its original position, basically making a full circle if you look at it where it's going.
I agree with a lot of your answer. Yeah, so we want to look at the position and what is happening in space, right? So this object is starting out at a position of 0. It's ending up at a position of 0. So we know it's going to end up at the same place that it started, right? It's going to travel 100 meters forward or up or some positive direction before it comes back. Now, there's a question in the chat here. Is it accelerating? And that is a really interesting question. In order to know that, we would have to know what its velocity is doing, right? So position-wise, right, it's moving away from the origin for 10 seconds, and then it's coming back towards the origin for 10 seconds. Velocity-wise, we know that initially it has a positive velocity because the slope of the curve is initially positive. Now, that being said, if you follow your finger along the curve, it is getting less and less steep, less and less positive. So the object is actually slowing down. And then right there at 10 seconds, right at the top of the curve, the tangent line would be horizontal. So the velocity right there is 0. It instantaneously, momentarily, it stops. And then the slope gets negative and it gets steeper and steeper negative. So at that point, it is speeding up in the opposite direction or in the backwards direction. Okay, so I mean, think about it just logically too. If something goes forward and then it goes backward, at some point it has to change its direction in order to go backwards, right? So right at that moment that it changes direction, it is momentarily stopped, just instantaneously, right? Its velocity at that moment, right at the top of the curve, is 0. Okay. So we can see that since the velocity is changing, right, it's positive and then it's slowing down to 0 and then it's speeding up in a negative direction, that yes, this object would be accelerating. Its velocity is changing.
Oh, I made a mistake of my answer.
Yeah, like I said, I agreed with almost everything that you said, except that
It
one.
was still speeding up. It was just in the negative direction. Where it slowed down was in the top.
Right. Okay. So just a quick review of the things that we had talked about today. Position time graphs, the difference between average velocity and instantaneous velocity, right? Average velocity, those 2 points of interest are separated on the curve. And then as they get closer and closer together on the curve, that turns into an instantaneous velocity. So the slope of that line that is tangent to the curve at that location, that is our instantaneous velocity, which we usually just call velocity. We can have all kinds of different shapes to our graphs, and we want to look at those slopes. If they're positive, then we have a positive velocity. If that slope is 0, our velocity is 0. And if the slope is negative, then we have a negative velocity. So here are some bonus activities for you guys to try if you would like to get some more practice with position time graphs specifically. Next week, we will move on to velocity time graphs and acceleration time graphs and how all three of those things are connected to each other. But here are 2 resources for you for position time graphs specifically. They are already published on Canvas, so you should have access to them. And like I said, I'll be posting answer keys for these tomorrow so that you can do them and check your work over the weekend if you would like to. But do you guys have any quick questions before we wrap up for the week?
Oh, it was my question in the beginning of the class.
Yes, we'll get back to that in just a minute after I stop the recording so that I can grab materials and things. But if you guys don't have any other questions, then don't forget about the enrichment session tomorrow at 10:30. Check the Canvas announcement for the Zoom link, and I will see you guys again on Monday. Have a great weekend.
You too. Thank you. Goodbye.
Bye.
Thank you, Professor.
Thanks.